Okay, we're looking for a technique that allows you to determine when a radical expression, in our case, a square root expression, is in simplest radical form. And basically, there's two primary methods. One is to search for perfect squares that are factors of the radicand, and another is to do what we call prime factorization, which I'll illustrate on the next board. But here's the kind of the thing you got to be aware of. If you have something like the square root of x to the sixth, you can take half this exponent to get the square root, which will be x cubed. And we're assuming in these examples that x and y, or the variables, represent positive numbers, so we don't have to worry about absolute value symbols. So if you have something like the square root of x to the seventh, I can't take half of that exponent evenly, so mentally I divide it into two factors. X to the sixth times x. I can take the square root of x to the sixth, as I showed up here, and get x cubed, and there's the simplest radical form for the square root of x to the seventh, x cubed times the square root of x. Similarly, for the square root of x to the fifth times y to the seventh, think of it like this. And you can take the square root of x to the fourth, which is this x squared. The square root of y to the sixth is y cubed. And these are the factors that remain under the radical, xy. So there's the simplest radical form for this expression right here. Now, when we're talking about finding or simplifying a radical expression where we have a number under here, there's basically two ways. Search for perfect squares that are factors of the radicand. And after you've done a lot of these problems, this probably is the easiest method. You just start to recognize them right away because you've done them so many times. But until you get good at that, or if the number is a big one like this one, I would determine the prime factorization of the radicand and then go from there. Okay, so here I've shown an example of finding the prime factorization of 9,720. I start by dividing by the smallest prime number that divides that number evenly, which is a 2, and I keep dividing by 2 until I can't divide by 2 any longer, and then I move to the next prime number, which is 3, and so on. And when the final quotient is a prime number, you know you're done. Okay, so I can rewrite 9,720 as 2 to the third. There's 3 factors of 2. There's 5 factors of 3, 3 to the fifth, and then 1 factor of 5. And then I use the technique I showed on the previous board. Rewrite 2 cubed as 2 squared times 2. 3 to the fifth is 3 to the fourth times 3. And then we have this 5. And we can take the square root of 2 squared, which is 2. The square root of 3 to the fourth, take half that exponent. 3 squared, those are the factors that remain under the radical. And 2 times 3 squared is 2 times 9, or 18. And here's kind of proof that these two radical expressions are equivalent. For the problem presented, the square root of 128, yeah, you could do this by realizing that there are some perfect square factors that divide into 128 evenly. As a matter of fact, you might right away recognize that 64 is a perfect square, and that's a factor of 128. The square root of the 64 is 8, and what remains under the radical is a 2. Okay, but if you don't see that, get the prime factorization of that radicand, and the prime factorization of 128 is 2 to the, this is supposed to be a 7. Rewrite that as 2 to the 6 times 2. Take the square root of 2 to the 6, which is 2 cubed, half the exponent. 2 remains under the radical. 2 cubed is 8. There you go, 8 radical 2. And here's kind of proof that these are identical. There you go. Hope that helped. If you have any questions, post a comment.